guys, it's Cherise. Today's video is an introduction to electrochemistry.
So today let's introduce electrochemistry and oxidation number. And before starting this unit, we need to get ready for some vocabulary. Words really are very important in redox chemistry. So the first word we'll talk about is that word redox. What do we mean when we say redox? Well, when we talk about redox, we mean a combination of two words, which is oxidation and reduction. Let's first look at this word oxidation and see what we have here. Here's a reaction between calcium and oxygen, where calcium is forming calcium oxide. You can see that calcium is losing electrons here as it meets oxygen and becoming the calcium 2+ ion in the calcium oxide. So two of these reactions where calcium loses 2 electrons are happening. In the second reaction here, which is the oxygen, it's actually gaining electrons, as you can see, to form those oxide ions. Okay, so here are our definitions. Oxidation will be a reaction in which electrons are lost. Just exactly what happened to the calcium in the reaction above. So a species which loses electrons, we're going to say is oxidized. It's a good way to remember that, and that is this word Leo. Say losing electrons is oxidation. Think about a lion, and you'll see the next part coming up quickly. So reduction is a reaction in which electrons are gained. So a species that gains electrons is reduced, and in the reaction above, that was the oxygen. Oxygen gained electrons from the oxide ion. So we would say oxygen was reduced. Gaining electrons is reduction. So here we have another easy mnemonic, and you can see here the lion, and the way to remember this is to say Leo the lion says grr. So losing electrons is oxidation, gaining electrons is reduction. So it's actually pretty clear where the word oxidation comes from. You can actually think about that for just a minute and you realize, well, oxygen is pretty good at stealing electrons. So having electrons stolen, we'll call that oxidation. So if you get electrons stolen, you were oxidized. How about reduction? Where does that word come from? Well, you might think about the experience that you would have if you were trying to refine, say, iron ore. So here we have a big pile of iron ore. It's a huge pile. And in this smelting and refining process, it gets refined, and now you have a small ingot of pure iron. So you had the iron ions were on the left. You had to put electrons onto them to make pure iron, and the overall mass was reduced. So that originally this word was reduction was the reduction in mass, but really we mean the gaining electrons. Our next topic is oxidation number. And the question we have is, well, how to track which compounds and species gain electrons and are reduced, and which compounds and species lose electrons and are oxidized. I mean, if oxidation and reduction is the whole deal here, we need to know what happens to what. So this thing about oxidation number, it's really an invented or calculated number, just a number, that tracks the gain and loss of electrons by an atom or ion through the course of a reaction. Okay, we are going to pretend that all bonding is ionic. Okay, all bonding is not ionic. We're going to pretend that it is. So pretend that it's all ionic. It's not. And we'll get a useful system this way. So if you don't mind, let's have a look and go back at our calcium and oxygen reaction yet again. So back to it. And we're going to see here what happened. First of all, the calcium met the oxygen. You got the calcium oxide here. And the calcium started as a neutral species, and so did oxygen. And later the calcium got a 2+ charge and oxygen got a - charge. So you would say here that calcium, look at this, it lost 2 electrons and it gained a positive change in charge of +2. And you would say that oxygen here gained 2 electrons and it gained a negative charge of -2. So we'd say calcium was oxidized because it lost electrons, and oxygen was reduced because it gained electrons. These little numbers here, which are showing the charges on the particles, are these oxidation numbers. So how to calculate oxidation numbers? Well, instead of giving you the rules and then saying, well, let's apply the rules, let me give you some samples and see if we can deduce the rules. So the first one here is magnesium. That one's oxidation number 0. It's in elemental form. Chlorine gas, also oxidation number of 0. It too is in elemental form. Here we have sodium oxide. Sodium's at a +1 charge and oxygen's -2. In these ionic compounds, it's pretty easy to work out the charges. Here in nitrate, oxygen will have a -2 oxidation number and nitrogen a +5. We'll get back to that one in a second for the rules. Look at nitrite ion. Here we have oxygen at a -2 and nitrogen at a +3. The next one is sodium sulfate. Now, sodium we know will have a +1 charge. There's 2 of those involved here, and the sulfate ion will have a -2 charge. So sodium is at +1, and the oxygen will be at -2, and the sulfur at +6 for the oxidation number. Finally here, the magnesium hydrogen phosphate or magnesium dihydrogen phosphate, magnesium at 2+, and the oxygen will be at -2, hydrogen at +1, and phosphorus at +5. So here are the rules. Aha! In case you wonder, where did all those numbers come from? Remember, we're pretending all the bonding is ionic. And in doing so, we're going to assign these numbers which represent the state of gained or lost electrons. So first of all, first rule, natural or unbonded state compounds have an oxidation number of 0. Second, oxygen has an oxidation state of 0 when it's diatomic, -2 when it's the typical 2- ion, and -1 if it's a peroxide. Okay, hydrogen will have 0 if it's H2, and it'll be +1 otherwise in all cases except metal hydrates where it'll take a -1 oxidation number. So in calcium hydride, we would have hydrogen as a -1 oxidation number. Fourth rule, the sum of the oxidation numbers multiplied by the subscript is the charge on the compound or the ion. It also suggests you can separate the ions from an ionic compound if that's easier to deal with, and that's what we saw in those examples above. And the final rule here is that we should start with the most electronegative atom present first. Now, typically that's oxygen, unless you're in a compound, of course, where there is no oxygen. So let's have a look at one example of that one. Here we have ammonia, and nitrogen is more electronegative than hydrogen, so it starts at -3, hydrogen at +1. And in the Fe3O4, oxygen takes its -2, and iron has to make up the difference at +8/3, so you'll get a total net 0 on this one. Let's see it in action. Here's a reaction between sulfurous acid, iodine, and water, and we'll try and figure out which atoms are oxidized and reduced. I'll just put in all the oxidation numbers here for all the various constituents in this reaction. And we'll see that the sulfur went from a +4 to a +6. It had a +2 change, so it was oxidized. Its oxidation number went up. Sulfur was oxidized. Iodine went from 0 here to -1, and it did so by gaining electrons and was thereby reduced. Iodine was reduced. We can split this reaction then into half reactions. That is one reaction that shows everything that was oxidized, and the other one where it was reduced. So here's the oxidation reaction. The sulfite ion made sulfate ion. Get some water in there to balance the oxygens, hydrogen to balance the hydrogens, hydride ions on the right-hand side, and electrons to balance the charge. Now the reduction reaction, notice that iodine gained 2 electrons here, and it's the same 2 electrons that were released in the oxidation reaction above. So the net total redox reaction is the one here, and that's about enough for one day. We'll get into half reactions quite seriously next time and make sure we get some practice done on oxidation number. Thanks, everyone. Have a look at the next 2 videos for more, and stay tuned for our next lesson where we get into redox half reactions.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.